Today we are going to see one important segment of the circular motion that I had discussed with you, that this is generally like many teachers teaches in the work for energy chapter, but I'm hoping that you know the idea of work for energy, the basics, and with this assumption I'm discussing this vertical circular motion. Okay, so of course you need some basic framework of the work for energy chapter, then only you can learn this part. Okay, so in the circular motion we are just remained with the two concepts. One is this vertical circular motion, and at the end we are going to discuss the rotating frame and of course the centrifugal force, Euler force, and the Coriolis force. Okay, so these pseudo forces we have to discuss, that one segment we have to explore, and this vertical circular motion we have to explore. Okay, so right now we are going to start with the vertical circular motion. Okay, so let's see guys. Suppose this is a this is a string. Okay, 1 minute guys. Okay, just let me put it here. And guys, this is a bob. Okay, or you can say a particle which is attached to this. Okay, which is attached to this, and this is your support, let's say uh, C. Okay, this is your support. The length of the string is, let's say, L, and what we are interested in, let's say if you give some velocity v to this particle. Okay, if you give this particle some velocity v horizontally, the particle is constrained to move in the circular path only. And right now we are giving the velocity in the in this horizontal direction. Due to this velocity guys, what will happen, the particle will, if you see, the particle will go like this, and then of course like this, something like this, on a circular track it will follow, because it is constrained to do so, like this way. Okay, it has to follow this kind of a path where the length of the string should not change, and of course that path possible is what, the circular motion only. Okay, so I'm interested in to find out what would be the velocity at any point of time, if let's say when the particle has covered some theta angle from the vertical. Okay, what would be the velocity it would be having at this moment, and what would be the tension in the string at this moment. Okay, what would be the tension in the string at this moment. These two things I am interested in, assuming that the velocity in the start is v naught, and let's say later your velocity is what, v, and tension is what, t guys. Okay, so let's try to find out these two values. So it's very simple guys. If you see, the thing is, uh, here there are how many forces are acting on this particle. If you see how many forces are acting, so there are three forces, we can say, sorry, only the two forces are acting on this particle guys. One is what, the tension, and the other one is what, mg. Here also guys, tension and mg, tension and mg. So these are the two forces which are acting on this particle, and due to that guys, this particle is able to move in the circle. Okay, now our concern is that what would be the velocity. So if you see here, if I want to apply the work energy theorem, what we can say, we can say that because the work done by tension force, okay, the work done by tension force on the particle will be always what, zero, because if you see, the force and the displacement is always what, perpendicular. So the tension work will be what guys, at every instant will be what, zero. So the work done will be only by what, by the mg. Okay, so if you see how much work done happened by the weight of the body. So if you see, the particle has gone up to this much height. Okay, particle has gone up to this much height. This height would be how much, if you see, if this is L, this will be what guys, this will be, you can say, this is L cos theta. Okay, you can see this uh, right angle triangle. Okay, with this right angle triangle guys, if this angle is theta, we can say this is what, L cos theta. So using this simple result, guys, we can say the height that it has gone is nothing but what, L minus L cos theta. Okay, so the particle has gone up to a height of what, guys, L minus L cos theta. So using the work energy theorem, as we know, it is equal to what, work external plus work internal is equal to change in kinetic energy. Work internal is what, guys, 0 if you consider the string plus what, the particle as a system. Then string work done is what, 0, because there is no work done is happening in the by the tension, okay, on the particle. So there is no work done happening here, only work external is happening, and that work external is, guys, nothing but what, it is mg L minus L cos theta negative. Okay, why? Because if you see, the body is going up, but the gravity is acting continuously, guys, what, downward. If you see, the body is going, guys, what, up, but mg is acting what, continuously downward. So of course the work done will be what, guys, negative, and that is equal to what, guys, the change in kinetic energy. So the, guys, final kinetic energy will be what, half m v square minus half m v naught square. Okay, so using this equation, guys, what we can say, that let's say you cancel the masses, okay, and what we are remained with is, guys, v square is equal to under root of sorry, v naught square minus 2gl 1 minus cos theta. So, guys, the velocity at any point of time will be how much, under root of v naught square minus 2gl 1 minus cos theta. Okay, so this is a general velocity that you can remember. Okay, if you want, if you don't want to remember, you can derive it, not a problem. Sometimes what I have observed, that if you remember this result, I think it helps if this kind of a typical problems come in front of you. This equation directly brings you what, towards the result. Okay, it can save a lot of time of yours. Okay, so like in my suggestion, if you can remember, please remember it. Okay, generally I don't like advise to remember anything, but what I felt, so that it's important. Okay, now coming to what, guys, the calculation of what, tension. Okay, so if you see, guys, right now the uh, let me make the FBD of the particle at this moment. Okay, so let's see, right now there is this mg force is acting, and this tension is acting in this direction. Okay, this tension is acting in this direction. If this is theta, guys, this angle will be also what, theta. So what we can say, this component will be what, mg cos theta, and this will be what, guys, mg sin theta. So we know that if a particle is performing a circular motion, it needs to follow the centripetal condition, okay, that we have discussed in the earlier lectures. Okay, so, guys, here also this condition has to be fulfilled, that the net force that acting on a body should be towards the center of the circular path, and that should be equal to what, at that moment, mv square by r. Okay, so let's use this centripetal condition idea here, guys, and let me write down the expression. So if I write down, guys, it will be what, it will be T minus mg cos theta, which is the net force towards the center, and it should be, guys, equal to what, m v square divided by L. Okay, so using this, guys, if I want to calculate the tension, it will be nothing but what, mg cos theta plus m by L. Guys, let me put the v square value here. So v naught square minus 2gl 1 minus cos theta. So if we solve this, guys, what we will get, so if you see, guys, it will be mg cos theta plus mv naught square by L minus 2mgl 2mg, sorry, okay, 2mg, and minus plus m, sorry, 2mg cos theta. Okay, so, guys, if I sum up everything, what I will get, t is equal to 3 mg cos theta 3 mg cos theta minus 2 mg plus mv naught square by L. Okay, so guys, this is the result that we got for the tension. Okay, so guys, this two equation, okay, this is I have derived for a general situation. These two equations, if you can remember, good, otherwise you can derive it if the problem comes in front of you. Okay, but usually I remember these two equations because it helps me solving the problems. Okay, so if you can remember, it's good. If you can't remember, you can derive it. Okay, not a problem. So t is equal to what, 3 mg cos theta minus 2 mg plus mv naught square by L, and v is equal to what, guys, square root of v naught square minus 2gl 1 minus cos theta. Okay, now guys, see, there are some special cases, okay, that we have to explore here. Okay, there are some special cases that we have to explore. So let's discuss, guys, one by one each of the part. Okay, so guys, you can say case 1. Okay, so these are basically the problems only. Okay, these are basically the problems only, but in general, in the uh, coaching, okay, industries, people discuss these as a what, as a cases. Okay, so I'm also discussing like this way only. Okay, but in general, if you see, it is actually a problem. Okay, it's a problem statement, nothing else. So the question is, if somebody asks you, is, guys, that what should be, what should be the minimum velocity we should give the particle, so that, so that it can, it can do the full circle, full circle. This is the problem, is okay. So what should be the minimum velocity we should give the particle so that it can do the full circle? Now some people say like case 1, that v minimum for doing the full circle. Okay, so both the ways are fine for me. Okay, let's discuss the problem. Okay, so guys, if you see, the thing is, if you see here, the, let's say the particle is right now here. Okay, particle is right now here, guys. Okay, and this is your support system C, length is what, L. So the concern is what, guys, that when it goes, okay, when it goes like this and it wants to complete the circle, it wants to complete the circle, it it should, guys, what, it should always follow the what, centripetal condition. Okay, if it is following the circular path, guys, everywhere the centripetal condition should be what, fulfilled. Okay, if the centripetal condition is not getting fulfilled, then the problem is going to happen. Okay, so guys, let's try to understand. The thing is, we know that, guys, here if you see, when the particle goes from here to here, just let me show you some detailings, okay, so that it can stay in your mind. So guys, if you see, if you just focus on this region, okay, if you just focus on, guys, what, this region, in this region, anywhere if you take the string, okay, anywhere if you take the string, okay, anywhere if you take the string here, guys, what will happen, that mg is going to always have, guys, what, one component along this. Okay, one component along this, and due to this region, guys, the tension, if you even, guys, if you go up to what, just below the 90-degree also, guys, you will be having what, you will be having some small component, okay, along this direction. Okay, I hope you're getting my point. Some components you will be having along this direction, but if this is the case, guys, what we can say, we can say that the tension never be zero in this lower half. Okay, in the lower half, tension can't be zero in the string. Okay, tension can't be zero in the string. Okay, this is one thing that you should keep in mind. Okay, now the thing is, suppose, guys, when the string goes in the upper segment, okay, when it goes in the upper segment. So if you see here, the thing is, when the particle is here, the mg, it is guys what, if you go here, if you see, mg is having a bigger component, okay, mg is having guys what, a bigger component towards the center, okay, mg is having what, a bigger component towards the center. So guys, if this is the case, if this is the case, if you see, if you go more closer, okay, so mg is almost what guys, you can say it is replacing the tension, okay, means what we can say, that the tension requirement, okay, see, what we have understood till now guys, that centripetal force that you need towards the center, it should be equal to what, your mv square by r, okay, centripetal condition. Now guys, if you know that, if as the particle is going up, as the particle is going up, velocity is decreasing, velocity is what guys, decreasing. And if velocity is decreasing guys, of course the force needed towards the center is also what guys, decreases, okay, the force that is needed towards the center is also decreases. So guys, in this case what we can say, because mg component towards the center is increasing, okay, the mg components towards the center is what guys, increasing, automatically the tension value will be what guys, decreasing, okay. And guys, as the particle will reach at the topmost point, at the particle will reach at the topmost point guys, your mg will be what, at its maximum, okay, mg will be what guys, at its maximum. And guys, if you want to do the circular motion, okay, if you want to complete this circular motion thing, what should be the criteria guys, listen me carefully now, okay. So guys, here if you see, when the particle is at the topmost point, the mg is completely acting towards the center, okay. And now guys, if tension is, if tension is almost equal to zero, not completely zero, not completely zero, I would say, I would say a little bit tension is there, okay, means just for the critical condition, so that the string does not slack. If at this moment guys, if your velocity becomes zero, just listen me, okay, if your velocity becomes zero here, what will happen, the mg is what, due to mg guys, body will what, fall down, okay, due to this mg guys, body will what, fall down. Otherwise you should have some force this direction, then only what, you can balance these two things, okay. But the thing is, because this mg is acting in this direction, and there is no way that you can balance this out with the centripetal condition, you can't handle this thing, okay. If you have a little bit idea of centrifugal force, you should understand guys, if you see from the rotating frame, there should be a centrifugal force which should be balancing this thing, okay. But let's say if you don't know the centrifugal force idea, still you can, you know that guys, that centripetal condition should be fulfilled, okay. So to fill the centripetal condition, if mg is the minimum possible force that is acting towards the center, you should have minimum some velocity, so that you can balance this by the following centripetal condition, okay. So it means, it means guys, that v equal to 0 is not a viable option, okay. You can't have this thing, okay. You should be, v should be what guys, not equal to 0. So means there should be a minimum velocity that you should have, so that you can fulfill the centripetal condition here. I hope you're getting my point, okay. So using this idea guys, what I can say is that mg should be equal to what guys, some value of minimum velocity at the topmost point to fulfill the centripetal condition guys. So mm cancel guys, okay, and using this what we can say, that v minimum needed is how much guys, under root of gl, okay. And here guys, what we are assuming, that the tension is almost what, equal to 0, means tension, the string is just going to slack, okay. The string has not slacked yet, but if we don't provide any minimum velocity there, then due to this mg, the body is going to what, slack, okay. So with this all idea, cumulatively we have understood that you should follow the centripetal condition, and the tension should just be nearly equal to 0, so that the string does not slack. And if there should be a minimum velocity, if this minimum velocity is not there, then due to this mg, the string is going to fall down, and string will slack. So to fulfill all these things, you should need a minimum velocity at the topmost point is how much, guys? Root GL. Okay, so if you have this much velocity, then you can perform the circular motion, because after that again you are going to get what? As you go down, guys, if you see, as you go down, okay, as you go down, guys, okay, the velocity is going to increase. And if velocity is going to increase, and if you see the mg component is towards the center is going to decrease, it means automatically the tension will appear here. Okay, tension will what, guys? Appear here. And then of course the string can't slack in this case. Okay, string can't slack. So I hope you getting the picture now that what is happening here. Okay, so the critical point of this trajectory is what, guys? Is here. Okay, this is the critical point or critical trajectory. Here if you make sure that body is able to follow the centripetal condition, afterwards it will be automatically what? Following the circular path and following the centripetal condition. So with this idea, guys, what we can do, we can simply find out the minimum possible velocity using the formula that we have developed earlier, guys. That is what? Under root of v naught square minus 2gl 1 minus cos theta. So guys, if you see at the topmost point when you reached, your velocity should be what? Root gl, and angle how much you have covered is what, guys? Theta is equal to pi. Okay, so if I put these two values, guys, here, it will become what? Root gl, if theta is what, guys? Is equal to the pi value. Okay, so guys, it will be what? Cos pi. So if I put these two, guys, what I'll get, guys, this will be what? GL, and this will be v naught square. Cos pi is minus 1, guys, so it will be minus minus plus 1, so 2, so minus 4gl. So guys, if I go on the other side, it will be what? 5gl is equal to what? V naught square. So v naught needed is how much, guys? Root 5gl. Okay, so guys, if you want to do the full circle, the minimum velocity that you should have at the bottom of the particle is how much, guys? Root 5gl. If this much velocity you are giving, then the particle is able to do the what, guys? Full circle. Okay, if velocity is more than that, it can do the full circle, of course, but in that case the tension at the topmost point will not be zero, it will be more than like zero, of course. Okay, so that is the one thing. Okay, now one more thing that might be asked here is that what is the uh, okay, I'll leave it, guys. So this is the first thing that we want to discuss. Okay, that how much velocity we need so that it can uh, do the full circle. Okay, now guys, the case second case is case 2. Okay, that let me discuss today, and the remaining part we will cover in the next lecture. Okay, so the second thing is what, guys? Case 2. Case 2 is what, guys? That what should be the maximum velocity we should give we should give we could give. Okay, could give, so that particle will never go in the upper half in the upper half of the circular path. Guys, this is the question. Okay, so the question is that what is the maximum velocity that we can give? Okay, what should be the range of the velocity, let's say, that we can give, so that particle will never go in the upper half of the circular motion, it should always lie in the lower half, or you can say it will just oscillate in the in the bottom or bottom half of the circle. Okay, like what I'm trying to convey here guys, if you see, just let me make the circle. So guys, if let's say this is your circle, so this is guys what, this is our uh, if you see, this is our upper half, okay, sorry, lower half. Okay, and what I'm interested in that how much how much how much velocity we can give maximum to this. Okay, so that it will oscillate in this zone only. Okay, it will oscillate in this zone only, it will never go in this zone. Okay, it should not go in this zone, that is our interest. Okay, so let's try to understand that also guys. So here you know that the particle will should not go in this upper half. Okay, if it has not to go in the upper half guys, the velocity when it reaches at the this point guys, it should be what, zero. Okay, if velocity becomes zero guys, when it just reaches, you can say when it just reaches what, here, and velocity becomes zero, it will never be able to what, go up, and it will what, it will come down. Okay, it will come down, and it will what, it will oscillate in this part. Okay, it will oscillate in this part. I hope you're getting my point. Okay, so with this idea guys, let's see that how do we get this thing. So it's a easy part only guys. Here what we can say, because we have qualitatively analyzed the condition, now we can just put the values and we can get that thing. So guys, here the maximum that particle can go is how much, 90 degree. Okay, not more than angular displacement should happen. Okay, so this is the thing that we should take care of during the calculation. So guys, what we can say, that the when it goes up to the 90 degree, at that point of time the velocity should be what guys, zero. Okay, means velocity should be non-zero. If velocity is non-zero, particle will go in the upper half. Okay, but if velocity is zero, it will be what, stay in the lower half only, or reaches to the boundary of the lower half. Okay, so in this case guys, what we can say, we can say that v is equal to v naught square minus 2gl 1 minus cos theta. So guys, if I put v equal to 0 is equal to v naught square minus 2gl 1 minus cos pi by 2, I can directly get the answer guys. So 0 is equal to v naught square minus 2gl, because cos pi by 2 is what guys, 0. So using this, what we can say guys, v naught should be equal to what, 2gl, if you want to just reach to the what, the topmost boundary. Okay, so to stay in the lower half lower half of the circle v naught max should never be greater than guys what, uh, root 2 gl. Okay, so it should be always less than or equal to what, root 2 gl, and of course it should be what guys, greater than 0. Then it will stay in the what guys, lower half. Okay, it will always stay in the what guys, lower half. So the maximum that it can have is what, root 2 gl. Okay, so from here guys, what we can conclude is that if if the v naught is less than root 5 gl. Okay, if v naught is what guys, less than root 5 gl and greater than root 2 gl, then it will it will goes in the upper half, but it will never be able to it will never be able to do the full circle. Okay, it will never be able to do the what is full circle. So now it should be our interest now, that how it will do the motion if 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 v naught is less than root 5 gl and greater than what, guys? 2 gl. Okay, so this analysis is very interesting, guys. Okay, when the velocity is what, more than root 2 gl, but it is less than what, root 5 gl. In this case, how the motion will be getting performed, that we want to explore. So guys, we will discuss this part in the next video. Okay, so this is, you can say, case 3. Okay, so we will see this segment, guys, in the next part, and maybe we can see some good problems after that, and then we can close this vertical circular motion part. Okay, okay guys, thank you.